Last time we started section 5.2, multiplication and division of integers, and today we're going to complete that section. When we left off last time, we had looked at the properties of integer multiplication, and we're going to add on a few more theorems regarding multiplication, and then we're going to eventually move into division here. Theorem 5.6 talks about what happens when you multiply a negative times an integer a. Excuse me. So what you see is that negative 1 times a is actually equal to the opposite of a. So multiplying by a negative changes the sign. It doesn't necessarily just mean positives become negatives. It actually also means negatives become positives. Theorem 5.7 is talking about what happens when we have a negative times a positive or a negative times a negative from another perspective. We saw this from an absolute value perspective last time. This one actually talks about the fact that if you have a negative times negative a, or an opposite of a times b, you could actually just multiply the a and the b together and then take the opposite afterwards, which is kind of how you process it probably anyway. And that if you have an opposite of a and an opposite of b, you can rather ignore the two negatives, right? A negative times a negative equals a positive kind of perspective. And then Theorem 5.8 actually talks about distribution across subtraction. And we had a similar theorem for whole numbers. It's exactly the same theorem here. It says that I can distribute the a through the subtraction just like I can through addition. The distributive property we actually had over here on part E, and it works exactly the same for subtraction as it did for addition. And the order doesn't make any difference if the a is being multiplied in front of the parentheses or in the back of the parentheses. All right, so now we're going to talk about integer division. It's very brief. The first thing is a definition. This looks very much like the definition of whole number division. For all integers a and b, a divided by b is the unique integer c if it exists, such that a is equal to b times c. And numbers help with this. We can use whole numbers as well as we can use integers for this, so it doesn't really matter. But let's say that we're using a negative in here just so that we're talking about values that maybe we weren't talking about before. Negative 6 divided by 2 is negative 3. And the reason is because 2 times negative 3 is equal to negative 6. In other words, there is a number I can multiply the 2 by in particular, right, that will get me back into the negative 6 form. And I think that you've already seen this happen, but just as a reminder, this is exactly the reason division by 0 doesn't work, right? So if I try to do negative 6 divided by 0 and say that it equals something, let's just say it equals k for the moment, it equals something. The problem is that I'd have to be able to for sure say that then that 0 times that k value is equal to negative 6, and there's no way to do that. I can never multiply 0 by something and get back to negative 6. And this is exactly the reason. If you just wrote this down, I usually don't write things that are not true on my screen. Make sure you mark it out. This is the reason it doesn't work. Okay? We talked about 3 sections worth in chapter 4 about divisibility with whole numbers. And this is actually talking about divisibility with integers and the fact that it all works the same way. If a divided by b is a unique integer, right, then we would say that a is divisible by b, or equivalently b divides a. And it's written with that vertical notation that we saw back in chapter 4. So, for example, the one I did before, negative 6 divided by 2 is the unique integer negative 3. Then we would say that that 2 divides negative 6. Another repeat from before. This is why this section is so quick, is because it's almost all repeat. It's talking about integer inequality. For all integers a and b, a is less than b, written with that standard notation, right? Oh, it's over there actually on the other side. Written a less than b if and only if there exists a positive integer k, such that a plus k is equal to b. Okay, so in other words, if I would take negative 2 and say that it is less than 1, the reason I know that is because there is a number I can put right here that would make it equal to 1. What number would that be? Three. Yeah, it'd be 3. Negative 2 plus 3 is equal to 1. There it shows up. An equivalency statement, theorem 5.9, says for integers a and b, a is less than b, or equivalently b is greater than a, if and only if b minus a is equal to a positive integer, i.e. b minus a is greater than 0. So a moment ago, I used the example that negative 2 was less than 1. Whoops, that's terrible. That's better. What that's saying is that if I were to take the 1, the bigger value, and I were to subtract the smaller value, negative 2, whatever my answer is, it has to be bigger than 0. And what is 1 minus negative 2? It's 3. And 3 is bigger than 0, right? If you think about like a perspective of a number line, all we're saying is that if we take a point on the further right-hand side of the number line and subtract a point further to the left side, we're going to end up with a positive number, and that's a true statement. Theorem 5.10 is the most interesting thing that we have seen because it's actually something that's different than we had before because of negatives. So it says, let x and y and n be any integers. If x is less than y, then if I add an n, the inequality does not change. I can add n to both sides, and it does not affect the outcome of the inequality, right? It's still less than. The second one talks about what happens when we multiply by a negative 1. And I know that you guys remember that. So what happens to inequalities when you, I can't get it written in here, when you multiply by a negative 1? Yeah, they turn the direction opposite. So this would be negative x is end up being greater than negative y. And if we just use some numbers, I think you'll probably be okay really quickly. If 2 is less than 3, and I make it negative, right? Well, negative 2 is actually greater than negative 3. Think about a number line. Where are you on the number line? The negative 2 on the number line is further to the right than the negative 3. The third statement talks about multiplication of a number, any number, that's positive. So when I multiply by a positive number, what does the direction of the inequality do? Stay the same or switch? It stays the same. And we can use as an example that 2 is less than 3 as well, and choose any positive number. So let's say you multiply by 5. You get 10 and you get 15. Nothing changed on the direction of the inequality. Right? And then the last one says, okie dokie, but what happens if you multiply by a negative? Not just negative 1, we already did that, but any negative. And the reality is that any negative would do exactly what negative 1 does. So if I multiply by negative n, what does the direction of the inequality do? It switches. And we'll just do the same example. 2 is less than 5. And let's multiply by a negative 5. Oh, sorry, 2 is less than 3 is what I meant to say. Same example. And if I multiply by a negative 5, then I have negative 10 on the left. It's supposed to say negative. And I have negative 15 on the right. And negative 10 is bigger than negative 15. So the direction of the inequality switches. All right, example number 5 is an interesting one. There aren't any directions that say how you have to do the problem, kind of like the inequalities that you guys just got homework papers back on, where not inequalities, absolute values, where I said you could just use guess and check and it'd be okay. Maybe not super effective overall, but it would be okay. So what I'd like to do in this set is to show you sort of some non-guess and check things, in particular on part B that you might not have thought about. But let's take a look at part A first. There's a couple of different ways that you could do part A, so I'm open to suggestions. As you look at this problem on part A, what would you see that you think that you should do first? Annika, you look like you're trying to.
Both sides by -5.
And that's the one that people don't usually do. You could divide both sides by -5. I'll show you another option here in a minute. If you do, this very lovely cancels out, leaving you with the x minus 3 is equal to 1. What might you do next? Add 3. And you would find that x is equal to 4, right? Okay, so let's sort of change it up. If I didn't divide by 5, what might I do? Yeah, I might distribute. That would be a good place to start as well. So if I distribute instead, I have negative 5x plus 15 is equal to 5. Why is it positive 15? Yeah, I got two negatives I'm multiplying, right? Negative 5 and negative 3. Okay, what would I do next after I've distributed?
Subtract 15.
Yeah, I need to subtract the 15. All right, so I have negative 5x on the left. What is 5 minus 15 for the right-hand side? Negative 10. Did I change something funny?
Supposed to be -20.
Oh, it was negative 5 here at the beginning. No, that's what's wrong. Yes, I left my negative off here, so yes, it should be negative 20. So sorry. Okay, that's fixed now. I just left a negative out from the copying. And then what would I do with the negative 5x and the negative 20? I would divide by negative 5. Okay, so what is negative 20 divided by negative 5? That's 4. Okay, so two different ways of doing the same thing. And you should end up with the same answer unless you copy things down wrong like I did. All right, do you remember the question? I think Emma asked it last time, and I just flew right by it today when I was going over the problems that were graded, that talked about the fact that A minus B and B minus A were additive inverses. Check your head if you know what I'm talking about. Remember that? We said it's because they add to 0, right? They're additive inverses. Well, if you will take a look at x minus 1 and 1 minus x, that's exactly what's going on here. They're additive inverses. Agreed? So if one of those results is 5, then the other one is negative 5. If one of them is 7, the other one's negative 7. If one of them is negative 256, the other one's positive 256. They're the same thing, they're just the wrong signs, right? But otherwise, they match. So the signs don't match, but what happens when you square things where the signs don't match? When you square it, they're already opposite of each other. What happens when you square it?
If anything was negative, it's not positive.
Okay, so in other words, if these results had given me negative 5 and 5, and then I square them, what happens? They're the same. I get exactly the same thing. So the values currently that are in parentheses are opposites of each other. Yeah? But when I square them, they are the same. So it's very interesting. I make mention of it because it's very funny, the result that comes out of this. And we actually have to be aware of that. So as we're taking a look at this x minus 1 could actually equal 1 minus x. Like, that's a possibility, and this could be solved that way. The other possibility is that the x minus 1 could equal the opposite of 1 minus x. Let's just solve the first one, and then I'll show you what happens interesting with the second one. So we would add the x to both sides. So I have 2x minus 1 is equal to 1. I'd add my 1 This is as 2x is equal to 2. So what would x be? It'd be 1. But the second part's the part that's more interesting when I solve this. If I distribute that negative, what do you notice happens? Yeah, it changed the x to a positive and it changed the 1 to a negative. What do you notice about this equation? Yeah, the two sides are exactly the same. They're not different at all. And anytime you end up with an equation where both sides are the same, what that means is it doesn't matter what x is. If x is 5, it's going to work. If x is 10, it's going to work. If x is negative 256, it's going to work. It makes no difference because both sides are already matching. So what this tells you is that x is any integer. And in some sense, even without the work, that should sort of make sense. Because what we said is that the values are the same anyway. The only thing they could be different by is their sign, right? And then when I square them, that just eliminated the possibility that the signs are different. They're both going to be positive. So any value is going to make this work. And this is the algebra support showing that any value is going to make this work. So maybe I should have written this in. I shouldn't have just assumed it maybe, but I'm square rooting is what I'm doing. And when you put the square root, you put the plus or the minus. That's why that's happening. And it's happening because they're inverses of each other, additive inverses of each other. So depending on your algebra perspective versus your conceptual perspective of inverses, that's another thought. Okay? All right.